Hi, my name is Michael Radushkin, and this is Lab 5, Magnetic Braking with Faraday. The presentation will go as follows: a brief introduction, followed by the experiment, followed by the computational model, and ending with a discussion. Lab is to determine how long it takes for a bar magnet to go through an aluminum tube, which allows us to see Faraday's law in action, and the experimental and computational times are shown. Some physical principles we use throughout the lab include the Biot-Savart law, that basically allows us to compute the magnetic field of a magnetic dipole in any position, Faraday's law, which equates EMF to the change in flux over time, Lenz's law, which the diagram shows to the left, that the induced magnetic field will oppose the increase or decrease in flux, some basic kinematic and kinetics formulas, and Ohm's law, which equates the potential difference to the current times resistance. And now on to the actual experiment. The system of this experiment is the bar magnet that will drop through the roll, and the surroundings are the aluminum roll, which will provide a magnetic force to the bar magnet, and Earth providing a gravitational force. The initial conditions of this lab include the mass of the magnet being 0.02 kilograms, the magnetic dipole moment being 2.781 as computed from lab 3, the tube length being 0.31 meters, the outer roll radius being 0.027 meters, and the foil width being 0.007 meters. The experiment basically involves setting up a magnet at the top of an aluminum roll and dropping it and recording the time that it takes for it to reach the bottom of the roll. And through 5 runs, we found that it took, on average, 1.31 seconds for the bar magnet to go through the aluminum roll. Now onto the computational model. The full model can be found online through the link in the description, but I'm just going to point out some key concepts here. We have a function for computing the dipole using the Biot-Savart law, and that was taken from the Lab 3 model. We have a function to calculate the change in flux over time using the equation that was provided within the physics video, where this p-value is the radius of the ring, and the y value is the distance between the bar magnet and the ring. And also using Ohm's law, we're able to take the result of this calculated change in flux value over time, because that value is equal to EMF. So it's EMF divided by the ring resistance, and that gives us the current. And now we're able to use that current in order to calculate the value of the magnetic force. And because the force from the bar magnet onto the loop is the same as the force of the loop onto the bar magnet, we're able to use the formula provided in the video in order to calculate that value. This is the end result of our computational model, where we've determined that the time that it takes in the tube is 1.341 seconds. Now some post-lab questions. Some possible errors that could have changed the value from the true value of the time it takes for the bar magnet to get through the aluminum roll includes not stopping the timer right when the bar magnet got out of the tube, and also not dropping the magnet straight down with only z direction velocity. So now also, here are some questions. Why couldn't we use a ferrous tube? Because the iron in those tubes could actually create an induced magnet, and that would interfere with our ability to observe the current induced magnetic field and magnetic force that this lab is trying to explore. And what happened to the magnet as it fell through? Obviously, the magnet fell slower in that space because of the magnetic force that was pushing the magnet up, that was counteracting the gravitational force. So in this case, in the model, red represents a counterclockwise current, while blue represents a clockwise current, as this is the only orientation that allows both the current above and below the magnet to provide an upwards force to counteract the gravitational force. And if we were to flip the magnet before we dropped it, it would still fall at a slowed rate. However, the red and blue currents would simply just be flipped to still provide an upwards force to counteract the downwards gravitational force. And the total time in the tube was slightly greater than the computational model. And the way we can make our computational model more accurate is simply by adding more rings to it. So as the graph shows, in the first part of the drop, the forces were not equal to each other, and thus there was a difference in velocity. However, during the time between 0.2 seconds and 1.2 seconds, the forces equaled each other, and thus the velocity didn't change. But at the end, the velocity changed because of the magnetic force dropping out. And if our resistivity was reduced as close as possible to 0, that would greatly increase our current according to Ohm's law, which would greatly increase the magnetic field, thus increasing our magnetic force, and thus the magnetic force potentially being able to balance out the gravitational force. And the magnet would never drop out of the aluminum roll. And if we had holes or slots in the tube, it would disrupt the flow of the current and decrease the magnetic force. Thus, the bar magnet would fall quicker.